Before the microchip. Inside every modern computer is a world that cannot be seen with the naked eye. Beneath the heat spreader of a processor, beneath the polished metal package, lies a piece of silicon covered with structures so small that billions of them can occupy an area no larger than a fingernail. These transistors switch electrical signals, store temporary values, control logic, move data, and coordinate every operation that makes a computer feel alive. They are arranged in layers, connected by microscopic metal lines, and fabricated with a precision that would have seemed impossible to the engineers of the 1950s. Yet, before anyone could place billions of transistors on a chip, someone first had to solve a much more basic problem. How do you make one transistor reliable enough, flat enough, and repeatable enough that thousands of others can eventually be built beside it on the same surface? The answer did not come from a famous personal computer company. It did not begin with Intel, the microprocessor, or the first home computer. It began in an era when even the transistor itself was still a young invention, when semiconductor laboratories were learning how to control silicon, and when engineers were struggling with a problem that seemed almost mundane compared with the future it would unlock. The man at the center of that problem was Jean Hoerni, a physicist whose name is far less familiar than those of Robert Noyce, Gordon Moore, or Jack Kilby. Hoerni did not build a machine that appeared in millions of homes. He did not create a famous consumer product. He created a manufacturing idea. And because manufacturing is usually invisible to the public, the importance of his contribution is easy to miss. To understand why Hoerni's work mattered, we have to return to a world before the microchip. Early electronic computers depended on vacuum tubes. These glass devices could switch and amplify electrical signals, but they were large, hot, fragile, and power-hungry. A computer built from thousands of tubes could fill a room and require constant maintenance. Tubes burned out. Cooling systems struggled. Power consumption was enormous. The machines were impressive, but they were difficult to scale. The transistor changed that. Invented at Bell Laboratories in the late 1940s, the transistor offered a smaller and more efficient way to control electrical current. It could perform many of the switching and amplification functions of a vacuum tube, without the same physical bulk. Engineers quickly recognized that transistors could make radios smaller, military electronics more reliable, and computers more compact. But early transistors were still individual components. Each one had to be fabricated, packaged, tested, and then physically connected to other parts. Even if a transistor was small, a machine requiring thousands of them still required thousands of connections. That was the next great obstacle. Electronics could not become truly miniature if every component still had to be handled separately. The future demanded a way to manufacture many devices together. By the mid-1950s, semiconductor companies were experimenting with ways to form transistors directly in silicon wafers. Engineers discovered that silicon could be heated in an oxidizing environment to produce a thin layer of silicon dioxide on its surface. This oxide was electrically insulating and could be used as a mask during diffusion. Openings could be created in selected areas, impurities introduced into the exposed silicon, and different electrical regions formed inside the wafer. In other words, engineers were beginning to use chemistry, heat, and patterning to draw electronic structures into silicon itself. But the process was still difficult. One important design was the Mesa transistor. The name came from its shape. Parts of the silicon were etched away so that the active transistor region stood above the surrounding material like a flat-topped hill. These devices could perform well, but the exposed edges of their semiconductor junctions were vulnerable. Contamination, moisture, handling, and surface effects could change their electrical behavior. A transistor could work beautifully in the laboratory and then fail later. That was unacceptable for applications that demanded reliability. Fairchild Semiconductor was one of the companies confronting this problem. Fairchild had been founded in 1957 by 8 engineers who left Shockley Semiconductor Laboratory. The group included Robert Noyce, Gordon Moore, Jean Hoerni, Julius Blank, Victor Greenwich, Eugene Kleiner, Jay Last, and Sheldon Roberts. They became known later as the Traitorous Eight, but at the time they were simply ambitious engineers trying to build better silicon devices. Fairchild was a young company entering a rapidly growing market. Its early customers included military and aerospace programs, where reliability was essential. A failed transistor in a consumer radio might be inconvenient. A failed transistor in guidance or communications equipment could be catastrophic. Fairchild needed devices that could survive real-world conditions. Jean Hoerni looked at the Mesa transistor and saw the weakness clearly. The delicate PN junctions, where regions of differently doped silicon met, reached the surface of the device and were exposed. These junction edges were electrically sensitive. If contamination accumulated there, leakage currents could increase. If moisture reached them, reliability could suffer. The transistor's most important internal boundaries were protected deep in the silicon but vulnerable at the surface. At first, this seemed like a packaging problem. Perhaps better sealing would help. Perhaps improved handling would reduce contamination. But Hoerni began thinking at a more fundamental level. What if the surface itself could protect the transistor? The key material was already present in the manufacturing process: silicon dioxide. To most engineers, the oxide layer was a temporary mask. It helped control where impurities entered the silicon, but once its job was done, it could be removed. Hoerni saw something different. Silicon dioxide was not merely a tool used during fabrication. It could become part of the finished device. In late 1957, before Fairchild had fully developed the idea, Hoerni wrote down a concept that would later prove revolutionary. Instead of stripping the oxide away after diffusion, leave it on the surface. Let it remain over the sensitive junctions. Use it as a protective layer. The idea sounds almost trivial when described today. Do not remove the oxide. Leave it there. But at the time, this simple decision opened an entirely new path. The oxide could protect the junction edges from contamination. It could help stabilize the surface. More importantly, if the semiconductor device remained flat and covered, engineers could continue processing the surface with precise patterns. This was the beginning of what became known as the planar process. The name came from the geometry. Instead of building a transistor with raised mesa structures and exposed junctions, the planar process created the device from one side of the silicon wafer, keeping the surface relatively flat. The crucial regions were formed beneath the protective oxide layer. Openings could be created only where electrical contacts were needed. The concept was powerful because it solved more than one problem at once. It improved reliability, it simplified surface protection, it made precise patterning easier, and it created a surface that could support future layers and interconnections. Yet inventions do not become revolutionary the moment they are conceived. Companies have schedules, customers, production lines, and financial pressure. Fairchild was focused on getting existing products into manufacturing. Hoerni's idea had to wait. The delay is one of the most revealing parts of the story. Today, the planar process is recognized as a foundational step in semiconductor manufacturing. In 1957, it was simply one idea among many inside a young company fighting to produce reliable transistors. The future of the microchip was already present, but almost no one could see it. The flat surface that changed silicon by 1959, the weaknesses of mesa transistors were becoming difficult to ignore. Fairchild needed a solution that would not merely improve one batch of devices, but fundamentally increase reliability. Jean Hoerni returned to the idea he had recorded earlier. Use silicon dioxide not as a temporary manufacturing aid, but as a permanent protective layer. In January 1959, Hoerni prepared a patent disclosure describing his approach. Within months, he demonstrated a working planar transistor. The breakthrough was not based on a new semiconductor material or a completely new transistor principle. It was a new way of manufacturing. To understand why it mattered, imagine a silicon wafer as a landscape that engineers want to transform into an electronic circuit. The wafer begins as a carefully prepared slice of crystalline silicon. The surface is oxidized, producing a thin layer of silicon dioxide. That oxide acts as an insulator and a barrier. Next, engineers use a patterned mask to define where parts of the oxide should be removed. The exposed regions become windows into the silicon below. Through those openings, dopant atoms can be introduced. These impurities change the electrical behavior of selected regions of the silicon, creating the junctions needed for transistor operation. In older approaches, much of the oxide might be removed after its masking function was complete. Hoerni's insight was to preserve or regrow oxide so that the finished device remained protected. The junctions could terminate beneath the oxide rather than at an exposed, etched surface. Contact holes could be opened only where metal connections were required. The result was a transistor built into a protected, relatively flat surface. This solved the immediate reliability problem. The oxide reduced exposure of sensitive junction edges to contamination and moisture. Leakage currents could be lower and more stable. Devices could survive handling and packaging more reliably. But the deeper significance went far beyond one transistor. A flat, oxide-covered surface was easier to pattern repeatedly. Engineers could return to the wafer and perform additional steps with precision. They could open new windows, introduce additional dopants, deposit materials, and define new structures. The surface became a manufacturing platform. At the same time, another technology was developing that would become inseparable from planar manufacturing: photolithography. Photolithography uses light and masks to create microscopic patterns. The idea had roots in printing and photographic techniques, but semiconductor engineers adapted it for silicon. A wafer could be coated with a light-sensitive material called photoresist. A mask containing a pattern was placed above it. The idea had roots in printing and photographic techniques, but semiconductor engineers adapted it for silicon. A wafer could be coated with a light-sensitive material called photoresist. A mask containing a pattern was placed above it. Light exposed selected regions. After development, some areas of the resist remained while others were removed. The material beneath could then be etched or processed. This allowed engineers to define tiny features without positioning each one by hand. That mattered enormously. Traditional electronics were assembled component by component. Photolithography allowed many microscopic structures to be patterned simultaneously across an entire wafer. If the process was repeated with multiple masks, increasingly complex structures could be built layer by layer. Hoerni's planar surface was ideal for this kind of repeated processing. The oxide layer protected the silicon while also becoming part of the patterning system. Different regions could be opened, modified, sealed again, and connected. The transistor was no longer simply a separate object fabricated from silicon. It was becoming a pattern inside silicon. This shift changed the economics of electronics. If a wafer contained many identical transistor structures, the same manufacturing steps could create them all at once. The cost of oxidation, diffusion, lithography, and deposition could be spread across many devices. After processing, the wafer could be cut into individual dies, each containing a finished component. That is batch fabrication. Batch fabrication would eventually become one of the central economic engines of the semiconductor industry. A modern chip factory does not manufacture one transistor at a time. It processes entire wafers containing many chips, each chip containing millions or billions of transistors. The details have changed enormously, but the logic is recognizable. Pattern many devices together. Repeat the process with extreme precision. Separate them only after the complex structures are complete. In May 1959, Hoerni filed a patent application describing his method of manufacturing semiconductor devices. The patent drawings showed cross-sections of silicon, oxide layers, diffusion regions, and contact openings. To a modern eye, the diagrams look simple, yet they preserve the moment when semiconductor manufacturing began moving toward a form that could scale. The patent was not a blueprint for a modern CPU. Hoerni could not have anticipated the exact shape of a 21st century processor. But the basic manufacturing philosophy was there. Use a protected surface, create selected openings, modify the semiconductor through those openings, preserve insulation over the junctions, and make electrical contacts where needed. One reason Hoerni's contribution is less famous than many later inventions is that manufacturing processes are difficult to visualize. A microprocessor has a name. A personal computer has a screen and keyboard. A transistor can be held in a hand. A process exists as a sequence of steps. It is something a factory does. But manufacturing processes can be more influential than individual products because they determine what can be made at scale. Hoerni's invention gave Fairchild a better transistor. Fairchild introduced the 2N1613 planar transistor commercially in 1960. The company also licensed aspects of planar technology, helping the concept spread through the semiconductor industry. The impact grew because other engineers could improve it. Better oxide quality reduced defects. Improved photolithography created finer patterns. More precise diffusion controlled electrical properties. Cleaner fabrication reduced contamination. New metallization techniques improved electrical connections. The process created a platform for progress. The oxide also changed the way engineers thought about the semiconductor surface itself. In earlier devices, the surface often seemed like a dangerous boundary where contamination and unwanted electrical effects could interfere with carefully formed junctions. Hoerni's process turned that boundary into a controlled engineering layer. The surface could now protect the device, guide later processing, and support precise contacts. That change in perspective was essential. Semiconductor manufacturing was beginning to move away from the idea of shaping one component at a time and toward the idea of designing an entire sequence of transformations across a wafer. The wafer became less like a raw material and more like a programmable manufacturing canvas. Each mask defined where the next physical change would occur. Each thermal step altered selected regions. Each oxide layer preserved what had already been built while preparing the surface for what came next. The sequence is one of the deepest reasons the planar process became so influential. It made complexity cumulative. Engineers could add a new level of structure without destroying the previous one. And once that platform existed, Robert Noyce saw something even more important. Noyce understood Hoerni's planar process and recognized that the oxide layer did more than protect the transistor. Because silicon dioxide is an electrical insulator, metal conductors could potentially be placed on top of it without shorting directly into the silicon below. That observation opened the door to a new idea. If several transistors and other components could be fabricated in the same piece of silicon, and if metal lines could be deposited on top of the oxide to connect them, then an entire circuit could exist on one chip. This was the missing bridge between the planar transistor and the planar integrated circuit. The significance becomes clearer when compared with ordinary electronic assembly. Imagine building a circuit from individual transistors. Each transistor is packaged separately. Wires or printed circuit traces connect one package to another. Every connection adds size, cost, and the possibility of failure. Now imagine forming the transistors side by side inside the same silicon. They are already physically close. If metal lines on the surface can connect them, the need for many external wires disappears. The entire circuit becomes one manufactured object. Hoerni made the flat protected surface. Noyce saw that the surface could carry interconnections. Together, these ideas turned silicon from a material used to make components into a material that could contain systems. But ideas on paper still had to become working hardware. That challenge would fall to another Fairchild team, led by J. Last. The first integrated circuits did not emerge from a single inventor or a single company. Around the same time that Fairchild was developing its planar approach, Jack Kilby at Texas Instruments demonstrated an early integrated circuit built from components formed on one piece of semiconductor material. Kilby's work proved that multiple circuit elements could be integrated. Robert Noyce's approach at Fairchild, however, was closely tied to Hoerni's planar process and offered a practical method for connecting components with metal lines on top of an insulating oxide layer. The competition was not merely about who had the better idea, it was about manufacturability. A laboratory demonstration can prove that something is possible. A commercial technology must be repeated reliably at acceptable cost across many devices. Fairchild's planar process was well suited to that challenge. J. Last led a team working to turn the planar integrated circuit concept into reality. The engineers had to solve problems that sound simple only after they have been solved. How should individual devices on the same chip be electrically isolated from one another? How should resistors be formed? Where should metal interconnections run? How large should contact openings be? How could the process be repeated across a wafer without destroying earlier structures? Every step depended on precise control. In 1960, Fairchild engineers produced experimental planar integrated circuits. Some early devices contained only a handful of transistors and resistors. Compared with a modern processor, they were almost unimaginably simple. But the number of components is not what made them revolutionary. The important fact was that the circuit had been manufactured as a single structure. The transistor was no longer the final product. The circuit was. This changed the direction of electronics. Once several devices could be integrated on one chip, the next question was obvious. Why stop at several? Why not dozens? Then hundreds? Then thousands? The history of semiconductor technology became a race to increase integration. Small-scale integration brought a few logic functions onto a chip. Medium-scale integration added more. Large-scale integration pushed transistor counts into the thousands. Very large-scale integration eventually brought entire processors and complex memory systems onto silicon. At each stage, engineers faced new problems, but the basic manufacturing strategy remained related to the planar foundation. Pattern the wafer, protect selected regions, modify others, deposit conductors, repeat. This repeated patterning process became increasingly sophisticated. Masks multiplied. Alignment tolerances tightened. Feature sizes shrank. Clean rooms became cleaner. Equipment became more precise. The industry learned to control defects that had once been invisible. Photolithography became one of the defining technologies of semiconductor manufacturing. The concept is elegant. Light carries a pattern from a mask to a light-sensitive layer on the wafer. Chemistry turns that image into a physical structure. Etching, deposition, implantation, or diffusion then changes the underlying material. Another layer is added, another pattern follows. By repeating this sequence, engineers build complexity vertically as well as horizontally. The modern microchip is therefore not carved in one step. It is constructed through a long series of carefully aligned transformations. The planar process helped make that possible because it treated the silicon surface as a controlled platform. This manufacturing approach also changed economics in a profound way. Imagine two methods of building 1,000 identical circuits. In the first method, workers assemble each circuit from individual components. Every transistor is placed, every connection is made. Labor and complexity increase directly with the number of circuits. In the second method, one wafer is processed through a sequence of steps. Each step acts on many circuits simultaneously. Oxidation affects the entire wafer, lithography patterns many dies. Diffusion changes selected regions across all of them. Metal deposition covers them together. The cost of one process step is shared across a large number of devices. This creates enormous economies of scale. If engineers can shrink each circuit, more dies fit on a wafer. If yield improves, more of those dies work. If equipment becomes faster, more wafers can be processed. If feature sizes shrink, each chip can contain more functions without increasing physical size. This economic logic became inseparable from technological progress. The same logic also transformed quality control. When thousands of structures are created together, a defect in the process can affect many devices. but an improvement can also improve every device on the wafer at once. This gave semiconductor companies powerful incentives to understand yield. Engineers studied where defects occurred, how particles entered the process, how temperature changed diffusion, and how masks could be aligned more accurately. Manufacturing statistics became as important as circuit diagrams. A chip design might be brilliant, but if only a small fraction of dies on each wafer worked, the product could be too expensive to sell. The planar approach therefore encouraged a new relationship between design and manufacturing. Circuits had to be designed not only to function electrically, but also to survive the realities of fabrication. Over time, this discipline helped create design rules, practical limits defining spacing, widths, overlaps, and other geometries so that a circuit could be manufactured reliably. Modern chip designers still live within descendants of that idea, even though today those rules are handled through sophisticated electronic design automation software. A smaller transistor was not valuable only because it was physically tiny. It allowed more functions per chip and more chips per wafer. That lowered cost while increasing capability. This is one reason semiconductor progress became so rapid. Improvements in manufacturing produced better products, and demand for better products justified investment in even more advanced manufacturing. Fairchild itself became one of the breeding grounds of Silicon Valley. Engineers who learned planar manufacturing and integrated circuit design later left to form or join new companies. The knowledge spread. Robert Noyce and Gordon Moore eventually left Fairchild and co-founded Intel in 1968. Intel would initially focus heavily on semiconductor memory, then help popularize the microprocessor. But Intel's future depended on the manufacturing revolution that had already occurred. A microprocessor is fundamentally an integrated circuit containing the central processing logic of a computer. The architectural idea was revolutionary, but architecture alone cannot create a chip. The processor must be fabricated from thousands of reliable transistors connected by microscopic conductors. The Intel 4004, introduced in 1971, contained roughly 2,300 transistors. That number seems tiny today, but putting an entire programmable CPU on one chip required a level of integration that would have been impossible only a decade earlier. The 404 did not use Jean Hoerni's original bipolar planar transistor design directly. Semiconductor technology had evolved, and MOS processes had become important for dense digital logic. Yet the broader manufacturing philosophy remained descended from the planar revolution. Define devices through patterned layers on a wafer, protect surfaces, create controlled junctions, and connect structures through deposited conductors. The microprocessor was therefore a new invention built on an older manufacturing foundation. As microprocessors improved, transistor counts rose quickly. The Intel 8008 expanded capability. The 8080 helped launch the hobby computer era. The 8086 established an architecture that would evolve into the x86 family. The 8088 powered the original IBM PC. Later processors added protected modes, larger registers, caches, floating point units, branch prediction, superscalar execution, and eventually multiple cores. Each architectural improvement required more transistors. More transistors demanded finer manufacturing. The personal computer revolution was therefore not only a software or architecture revolution, it was a manufacturing revolution. A personal computer can be affordable only if its central components can be produced in enormous quantities at low cost. The CPU, memory chips, interface controllers, graphics logic, and storage electronics all depend on mass-produced integrated circuits. Without scalable semiconductor manufacturing, computing might have remained expensive and institutional. The planar process helped create the pathway from laboratory transistor to mass-produced chip. Its influence extended beyond processors. Semiconductor memory benefited enormously from planar manufacturing. Memory is especially dependent on density because a useful chip requires many repeated storage cells. Dynamic RAM, static RAM, ROM, EEPROM, and later flash memory all depend on the ability to create large numbers of microscopic electronic structures with extraordinary consistency. Graphics hardware followed the same path. Networking controllers did as well. Sound chips, USB controllers, chipsets, embedded processors. Every major subsystem inside a PC eventually became integrated. The motherboard that once needed many individual logic chips gradually required fewer, because more functions were absorbed into larger integrated devices. Integration transformed the computer from a collection of electronic parts into a small number of highly complex chips. And behind that transformation was a manufacturing philosophy that began with a deceptively simple idea: keep the surface protected and flat enough to build more. The forgotten invention. Beneath the PC revolution. By the time personal computers became common, Jean Hoerni's original planar transistor had already disappeared beneath layers of technological evolution. New transistor structures emerged. MOS technology became dominant in digital logic. Feature sizes shrank from micrometers toward nanometers. Designers gained computer-aided tools that could manage circuits containing millions of components. Yet the influence of the planar manufacturing revolution remained. This is one reason Hoerni's name is less famous than those of many people who came after him. History tends to remember products and personalities. People remember the Macintosh, the IBM PC, the Intel Pentium, and the iPhone because these are visible objects. Manufacturing processes are hidden inside factories. Consumers do not see oxidation furnaces, photolithography masks, dopant implantation, plasma etching, or thin film deposition. They see the chip after all of those processes are finished. As a result, the engineers who invent ways of manufacturing electronics can become almost invisible. Robert Noyce is remembered for the integrated circuit and for co-founding Intel. Gordon Moore is remembered for Moore's Law and Intel. Jack Kilby is remembered for his early integrated circuit demonstration. Jean Hoerni is remembered mostly by semiconductor historians. But without reliable manufacturing, brilliant circuit ideas remain difficult to commercialize. Hoerni's contribution was not that he imagined every future chip. It was that he solved a problem at the exact point where electronics needed a path from individual transistors toward integration. The planar process transformed the surface of silicon from a vulnerability into an asset. Before Hoerni, the exposed surface was part of the reliability problem. After Hoerni, the protected surface became part of the manufacturing solution. That reversal is the heart of the story. The silicon dioxide layer did not merely keep contamination away. It allowed engineers to define, protect, and connect devices on one side of a wafer. This made repeated patterning practical. Repeated patterning made integration practical. Integration made scaling practical. Scaling made modern computing economically possible. The chain is long, and no single step deserves all the credit. But remove the planar breakthrough, and the path becomes much harder. The relationship between Hoerni and Noyce illustrates how major technologies are often created. One engineer solves a problem for one reason. Another engineer sees a different possibility in the solution. Hoerni wanted reliable transistors. Noyce saw a way to connect multiple devices on the same chip. Jay Last's team figured out how to manufacture working planar integrated circuits. Other companies improved the processes. Equipment manufacturers built better tools. Chemists created better photoresists. Physicists improved transistor structures. Circuit designers learned to use increasing numbers of devices. The semiconductor industry grew not through one isolated genius, but through a chain of insights. This chain extended into Silicon Valley itself. Fairchild became a source of talent for dozens of later companies. Engineers left and founded startups. Those companies created new technologies, trained more engineers, and generated new spin-offs. The region's culture of rapid movement and entrepreneurship was partly built around semiconductor manufacturing knowledge. Intel emerged from that environment. So did companies involved in memory, processors, logic, and later graphics. The personal computer industry inherited this entire ecosystem. The personal computer made the consequences visible to ordinary people. A CPU that once would have required entire boards could now fit into one package. Memory that once occupied cabinets could be assembled from standardized chips. Graphics, sound, storage control, and networking could each migrate into increasingly dense integrated circuits. Every reduction in chip cost allowed computer manufacturers to offer more capability at a lower price. That affordability created larger markets, and larger markets justified more investment in fabrication. By the 1990s, semiconductor manufacturing had become one of the most capital-intensive industries in the world. A new fabrication facility required extraordinary spending, not because silicon itself was expensive, but because controlling microscopic structures at massive scale demanded advanced equipment, ultra-pure chemicals, filtered air, precise temperature control, and near-perfect process repeatability. The economic world surrounding the PC was therefore inseparable from the manufacturing world Hoerni had helped set in motion decades earlier. By the 1980s, semiconductor fabrication had become a highly sophisticated industrial discipline. Chips were manufactured using many photolithographic masks. Alignment had to be precise. Defect control became crucial because a microscopic particle could ruin a device. Clean rooms became symbols of the industry. Workers wore protective suits, not because the wafers threatened them, but because humans threatened the wafers. A single speck of dust could be enormous compared with the structures being fabricated. This inversion shows just how small electronics had become. Hoerni's early planar transistors were created with feature sizes that would look huge beside modern devices. Yet the basic challenge was the same. Keep the surface clean, control where materials go, and protect the structures after they are formed. As transistor dimensions shrank, engineers faced new physical limits. Electric fields became more intense. Leakage currents increased. Thin insulating layers approached atomic scales. Heat became difficult to manage. Planar MOS transistors, which had dominated for decades, eventually began giving way in advanced processors to three-dimensional structures such as FinFETs. A FinFET raises the transistor channel into a fin-like structure so the gate can control it from multiple sides. More recently, gate-all-around designs surround the channel even more completely. At first glance, these three-dimensional transistor structures seem to mark the end of the planar idea. But that conclusion would be misleading. The modern semiconductor process is far more complex than Hoerni's original method, yet it still follows the manufacturing philosophy that planar technology helped establish. A wafer is patterned. Selected regions are protected. Others are etched or modified. Insulators are grown or deposited. Conductors are added. Layers are aligned. The sequence repeats. The structures may now rise vertically, but the process remains a carefully orchestrated series of patterning steps across a wafer. Even modern photolithography would be recognizable in principle to early semiconductor engineers, though the equipment would appear extraordinary. Today's most advanced fabrication systems use extremely short wavelengths of light, sophisticated optics, vacuum chambers, complex masks, and computational correction techniques. Feature sizes are so small that the behavior of light itself becomes a major engineering challenge. Yet the fundamental goal has not changed: transfer precise patterns onto silicon. The complexity of a modern CPU is staggering. One chip may contain billions or tens of billions of transistors. It may include multiple processing cores, large caches, integrated graphics, memory controllers, security engines, AI accelerators, and high-speed interfaces. Above the transistors are many layers of metal interconnects that route signals across the chip. Every layer must align with the others. Every transistor must behave within tight tolerances. The entire device must be manufacturable not once, but millions of times. This is where the legacy of semiconductor process innovation becomes most visible. The extraordinary thing about a modern processor is not simply that engineers can design it, it is that factories can reproduce it reliably. A design containing billions of microscopic components is only commercially useful if a large percentage of manufactured chips actually work. That requires manufacturing discipline on a scale Jean Hoerni could never have imagined. But he helped define the path toward it. This also explains why the planar process should be considered part of PC history, even though it predates the personal computer by decades. The PC revolution depended on affordable chips. Affordable chips depended on batch fabrication. Batch fabrication depended on repeatable planar-style processing, photolithography, surface protection, and interconnection. The story of the PC therefore begins long before the first PC was assembled. It begins in the factory. It begins with a wafer. It begins with a surface, the flat surface that gave silicon a future return to a modern computer. A program opens. The processor reads instructions. Memory supplies data. Graphics appear on the screen. Storage responds. Network packets move through controllers. To the user, all of this happens instantly. The machine feels like software, but underneath the software is architecture. Under architecture is circuitry. Under circuitry is manufacturing. And under modern semiconductor manufacturing lies a history of seemingly small process decisions that made everything else possible. To the user, all of this happens instantly. The machine feels like software, but underneath the software is architecture. Under architecture is circuitry. Under circuitry is manufacturing. And under modern semiconductor manufacturing lies a history of seemingly small process decisions that made everything else possible. Jean Hoerni's decision to preserve silicon dioxide over sensitive junctions was one of those decisions. He did not invent the transistor. He did not invent the integrated circuit alone. He did not invent the microprocessor. He did not design the personal computer. His contribution was quieter. He found a way to manufacture transistors with a protected, flat surface that improved reliability and enabled repeated processing. That surface became the bridge to something larger. Robert Noyce realized that metal interconnections could be placed on top of the insulating oxide. Jay Last and his Fairchild team helped turn the idea into working planar integrated circuits. Manufacturers learned to produce them in volume. Engineers learned to place more components on each chip. The number of transistors began to climb. A few became dozens. Dozens became hundreds. Hundreds became thousands. Thousands became millions. Millions became billions. At every stage, the physical details changed. New transistor architectures appeared. New materials replaced older ones. Lithography advanced. Doping techniques improved. Metal interconnects became more complex. Lithography advanced. Doping techniques improved. Metal interconnects became more complex. Clean rooms became cleaner. Computer-aided design replaced hand-drawn layouts. Factories grew into multi-billion-dollar facilities containing some of the most advanced machines ever built. Yet one principle remained. The wafer became a platform on which microscopic structures could be built through repeated, precisely controlled layers. That was the manufacturing revolution Hoerni helped begin. There is something almost poetic about the simplicity of the original insight. Silicon dioxide was already there. Engineers already knew how to grow it. They already used it during fabrication. The breakthrough was partly about recognizing that the material everyone expected to remove could become useful if left in place. That is often how important inventions happen. The new idea is not always a new object. Sometimes it is a new relationship between existing things. Sometimes it is a different way to interpret a familiar material. Sometimes progress begins by refusing to remove something everyone else considers temporary. In Hoerni's case, the oxide became a shield. Then it became a manufacturing surface. Then it became part of an integrated circuit process. Then that process became part of an industry. The story also reveals why technological credit is complicated. Jack Kilby proved that integrated components could share one semiconductor substrate. Robert Noyce developed a practical planar integrated circuit concept using metal interconnections. Jean Hoerni created the planar transistor process that made Noyce's approach possible. Jay Last and his team implemented early planar integrated circuits. Many other engineers contributed isolation techniques, photolithography, oxide masking, diffusion control, and manufacturing improvements. Jay Last and his team implemented early planar integrated circuits. Many other engineers contributed isolation techniques, photolithography, oxide masking, diffusion control, and manufacturing improvements. No single person created the modern chip. The microchip is a civilization-scale accumulation of ideas, but some ideas sit deeper in the stack than others. Hoerni's planar process is one of them. Its influence is difficult to see because it became normal. Once an invention becomes part of standard manufacturing, future engineers stop thinking of it as revolutionary. It becomes simply the way things are done. That is perhaps the highest form of technological success. An invention becomes invisible because the world cannot imagine working without it. The same happened with the transistor. The same happened with integrated circuits. The same happened with photolithography. And the same happened with planar processing. Modern semiconductor engineers work with technologies far beyond what existed at Fairchild in 1959. They use advanced lithography, plasma processing, atomic layer deposition, high-K dielectrics, complex strain engineering, and three-dimensional transistor structures. The equipment is different. The physics is more demanding. The scale is almost incomprehensible. The same happened with integrated circuits. The same happened with photolithography. And the same happened with planar processing. Modern semiconductor engineers work with technologies far beyond what existed at Fairchild in 1959. They use advanced lithography, plasma processing, atomic layer deposition, high-K dielectrics, complex strain engineering, and three-dimensional transistor structures. The equipment is different. The physics is more demanding. The scale is almost incomprehensible. But the manufacturing mindset is familiar. Protect what must remain, expose what must change, pattern with precision, modify the material, add conductors, repeat. Build complexity one controlled step at a time. This is how a modern CPU comes into existence, not as one object assembled from billions of separate transistors, but as a wafer transformed through repeated processes until billions of devices emerge together. That distinction is everything. If each transistor in a modern processor had to be manufactured and connected separately, the computer age would collapse under the cost and complexity. The reason billions of transistors can exist inside a consumer product is that they are fabricated collectively. That is the economic miracle of the microchip. And the planar process helped make that collective fabrication possible. Think about the journey from Fairchild's laboratory to the modern PC. In 1959, Hoerni was trying to make transistors more reliable. A decade later, integrated circuits were becoming increasingly complex. By 1971, Intel had placed a programmable CPU on one chip. By the late 1970s, microprocessors were powering hobby computers. In 1981, the IBM PC helped standardize personal computing for business. Through the 1980s and 1990s, processor performance rose rapidly. Memory capacity expanded. Graphics became more sophisticated. Networking became essential. In the 21st century, computers moved into laptops, phones, vehicles, appliances, and data centers. The number of transistors exploded. The distance between Hoerni's planar transistor and a modern processor seems enormous. But the connection is real. In 1981, the IBM PC helped standardize personal computing for business. Through the 1980s and 1990s, processor performance rose rapidly. Memory capacity expanded. Graphics became more sophisticated. Networking became essential. In the 21st century, computers moved into laptops, phones, vehicles, appliances, and data centers. The number of transistors exploded. The distance between Hoerni's planar transistor and a modern processor seems enormous. But the connection is real. Every generation depended on the ability to manufacture more devices reliably on silicon. Without that ability, computer architecture would have reached a wall. Software would have demanded functions the hardware could not afford. Personal computing would have remained slower, larger, and more expensive. The digital world would look radically different. This is why the history of computing cannot be understood only through famous machines. It must also include the hidden processes that made those machines possible. The Intel 4s and 4 matters. The IBM PC matters. The transistor matters. The integrated circuit matters. But so does the method used to manufacture reliable devices in enormous numbers. Jean Hoerni belongs in that story. He stands at a turning point when silicon stopped being merely a material for individual transistors and began becoming a platform for entire electronic systems. His invention helped turn the semiconductor surface into something engineers could repeatedly pattern, protect, and connect. That is the deeper meaning of the planar process. It did not merely flatten a transistor. It flattened the path toward integration. And once that path existed, the semiconductor industry began an extraordinary climb. More transistors, more functions, more computing power, lower cost per function, smaller devices, larger markets. The process fed itself, better chips, created demand for better manufacturing. Better manufacturing created more powerful chips. The cycle continues today. There's another reason this history matters now. As transistor scaling becomes harder, the semiconductor industry is increasingly forced to revisit the relationship between architecture and manufacturing. Lower cost per function, smaller devices, larger markets. The process fed itself. Better chips created demand for better manufacturing. Better manufacturing created more powerful chips. The cycle continues today. There's another reason this history matters now. As transistor scaling becomes harder, the semiconductor industry is increasingly forced to revisit the relationship between architecture and manufacturing. Chiplets, advanced packaging, three-dimensional stacking, backside power delivery, and new transistor structures all represent attempts to continue the same old ambition by different means, place more useful computing capability into a limited physical space. The future may no longer depend on shrinking one flat transistor in exactly the same way as before, but it still depends on process innovation. Hoerni's lesson remains relevant because it shows that manufacturing breakthroughs can be as important as circuit inventions. When a physical limit appears, the answer may come not from a faster algorithm or a clever instruction set, but from a better way of building the device itself. That was true in 1959, and it remains true in the most advanced semiconductor laboratories today. Modern semiconductor companies spend enormous sums developing fabrication processes, because manufacturing still determines what computers can become. The industry is now approaching physical scales where individual atoms matter. Yet the ambition remains the same as it was in Hoerni's era. Place more reliable electronic function into less space. The tools have changed. The challenge has not. So when we look at a modern processor, we should not see only billions of transistors. We should see layers of history. The vacuum tube gave way to the transistor. The transistor moved into silicon. Silicon gained a protective oxide. The oxide supported planar manufacturing. Planar manufacturing enabled the integrated circuit. Integrated circuits enabled the microprocessor. Microprocessors enabled the personal computer. And the personal computer helped transform modern life. At the beginning of that chain stands a physicist in the late 1950s, looking at a fragile transistor and asking a practical question. How can this device be protected? His answer was not dramatic. Leave the oxide, protect the junction, keep the surface flat, build from there. It was a manufacturing solution to a reliability problem. But history often turns on solutions that seem small at first. Jean Hoerni did not know what personal computers would look like. He did not know that processors would one day contain billions of transistors. He could not have imagined smartphones, cloud computing, artificial intelligence accelerators, or the semiconductor factories of the 21st century. He did not need to. He solved the problem in front of him, and by solving it, he helped create a surface on which the future could be built. Hoerni's story also reminds us that the most important turning points in technology are not always obvious when they happen. A new process may look like a small improvement because it does not immediately create a new market. Its importance appears later when other inventions begin depending on it. The planar process gained power in exactly that way. It made better transistors, then better integrated circuits, then denser memory and processors, and finally entire generations of affordable computers. By the time the world recognized the scale of the transformation, the original manufacturing idea had already become part of the industry's normal vocabulary. That is Jean Hoerni's legacy. Not a famous machine, not a consumer brand, not a product sitting in a museum behind glass. A process, a flat layer of silicon dioxide, a protected transistor, a manufacturing idea. And beneath nearly every modern microchip, the echo of a simple decision that gave silicon a future.